Welcome to Module 8. This module covers Chapter 12 from your textbook. This chapter is about comparing several independent means. In previous chapter, we talked about independent sample t-test and paired sample t-test. Regarding independent t-test, we are comparing just two means. But here with ANOVA, we are comparing more than two independent means. So this is an example from your textbook. It's a puppy example. It says a puppy therapy RCT randomized controlled trial in which we randomize people into three groups. So here we have three independent groups instead of having two independent groups. So we have a control group, we have 15 minutes of puppy therapy and 13 minutes of puppy contact. Our outcome variable, our dependent variable is happiness. Happiness is a scale from 0 representing unhappy to 10 happy. The predictions, our prediction is, or in other words, our hypothesis is or are, number one, any form of puppy therapy should be better than the control. A dose response hypothesis that as exposure time increases from 15 minutes to 30 minutes, happiness will increase too. So these are our hypotheses or predictions for this study, for our research question. So here, this is our data. So on the left side, we have IDs. These are different people. So each row represents individual. We have those. So we have three groups. We have no puppies, 15 minutes with puppies, and 30 minutes with puppies. So we have three independent groups. And we have the happiness score, which is our dependent variable from 0 to 10. And we have group mean, group variance, and group standard deviation for each group. And at the bottom of the table, we have grand mean, grand variance, and grand standard deviation. So group mean or group variance or group standard deviation, these are like statistics for each group. But grand mean and grand variance and grand standard deviations are statistics for the entire data for all individuals in our data set. Grand mean, grand variance, and grand standard deviation, and all of these other statistics for each group are very important because we are gonna use them. If we want to like do ANOVA by hand, we will use these. But if SPSS does that for us, we don't need to calculate any of these statistics. Here is very important point. Remember, ANOVA, which stands for the analysis of variance, it's very similar to regression, to linear regression. So that's why here, although we have three independent groups, so the ideal is to run or to conduct ANOVA here. But as I said, linear regression model is very similar to ANOVA. So that's why we have a linear model for our research question. So happiness is our dependent variable. So like imagine is as a y variable. Happiness is y variable. And then we have three independent groups, and all those independent groups are our predictors or our independent variables. So we have beta 0, which is the constant, or it's the point at which the our regression line intersects with the y-axis. We have beta 1, which is for our long or our dependent variable, 30 minutes contact with puppies. And we have beta 2, that's the coefficient, beta coefficient for another independent variable, which is short or 15 minutes contact with puppies. And we have our error term. So we can create two dummy variables in order to put them in our regression model. Dummy variable 1 is long and dummy variable 2 is short, and 0 for both variables indicate control, which means no puppies. So dummy variable 1 is long or 30 minutes contact with puppies. So if it is 15 minutes of puppy therapy, we can just put it 0 for that. And for dummy variable, for 30 minutes of puppy therapy, we should put 1 for that dummy variable. So we can create two dummy variables in order to run regression model rather than ANOVA here. So control group is just the mean of the control group is our the constant term, or beta 0, which is the point at which the regression line cut the y-axis or intersects with y-axis. So for 30-minute group, we have to put 0 for the short. So beta 2, the beta coefficient for the second dummy variable should be 0. And the beta 1, or the coefficient for 30-minute group, will be the mean of 30-minute, the mean of the happiness for 30-minute therapy with puppies minus the mean of the happiness for control group. So we do the same thing for 15-minute group. And then we can just run the regression using the SPSS. This is the table, this is the output SPSS will provide for us if we want to run regression instead of ANOVA. But like whenever you run, if you remember from the regression module, we had a specific table with a title of ANOVA, and it provides the F statistics and the p-value. That's exactly the ANOVA. So for ANOVA, our statistic is F. In independent sample t-test, our statistics was T statistics. But for ANOVA, that's F. And that's why we can get the the ANOVA output from regression model. And also we will get coefficients because we are running regression here. So we get beta coefficient, and we get the p-value and then t statistic. So as you know, we have two different types of observation. We have or research or studies. We have experiments, or we have natural observation. So in natural observation, we are just looking at relationship or association between variables. We cannot, uh, infer causality here. But for experiments, because we are manipulating one variable, we can kind of indicate causality in experiments. For the ANOVA, we can use ANOVA for experiments. We can use ANOVA for randomized controlled trials, where we can infer causality. So this slide and a few slides is about how to calculate F statistic. I'm gonna skip this, but this is for your information. Because you don't need to calculate F statistics by hand. SPSS will do that for us. But this is the formula for F statistic, how we can get F statistics for ANOVA if we wanna work with data by hand instead of using SPSS. So as I said, ANOVA is the analysis of variance. ANOVA is a broad term, and there are different types of statistics falling under ANOVA. So we have like one-way ANOVA, we have two-way ANOVA, we have three-way ANOVA, and etc. We have ANCOVA, we have MANOVA. There are different types of ANOVA procedures. But here in this module, we will just focus on one-way ANOVA. So ANOVA, or analysis of variance, we are testing the differences between more than two means of independent groups. So we have more than two groups. We can use ANOVA instead of independent t-test if we have two groups. It's gonna give us the same output as independent t-test. So let's say in our puppy example, we had just control group and 15-minute therapy with puppies. So we have two independent groups. Instead of running ANOVA, instead of running independent t-test, we can run ANOVA here, and the output will be the same. But if we have more than two independent groups, we cannot run independent t-test. We should run ANOVA. Or we can run multiple independent t-tests. But there is another problem with that. If you remember, we talked about the alpha inflation. So if we want to run multiple independent t-tests instead of just running one ANOVA, we have to correct for our alpha. We can use Bonferroni alpha correction in order to prevent from alpha inflation. But honestly, it's better to use ANOVA instead of like using multiple independent t-tests and then just correct for alpha. So for ANOVA, our dependent variable should be either interval or ratio. If our dependent variable is not interval or ratio, we can use the non-parametric version of ANOVA, which we will talk about that later. So as I said, there are different types of ANOVA. We have one-way ANOVA, we have two-way ANOVA, but here we are gonna focus on one-way ANOVA. So in one-way ANOVA, we have grouped subjects in only one way instead of like two ways. ANOVA is just a special case of the linear model. That's why in SPSS deals with ANOVA as the general linear model, or GLM. And that is why this module's title is GLM1. So the response variable is the variable you are comparing. The response variable is our dependent variable. That's our y variable. So it's also called response variable. That is the variable we are comparing. The factor variable, those are our groups. Those are our independent variables. And those are categorical variables being used to define the groups. So we call one-way ANOVA one way because each value is classified in exactly one way. So for example, our comparisons can be by gender, by race, by political party, by color, and etc. So we are comparing independent means in one way, by gender, for example, by race, by education level, by political party. But if we want to compare the means by gender and race, by race and education, that will be two-way ANOVA. So when and why? When we want to compare means, we can use a t-test. But as I said, t-test has some limitations. We cannot use t-test for more than for testing for the difference among more than two independent means or independent groups. That's one limitation. Another limitation is it can be used only with one independent variable. Independent t-test we can just use with one independent variable. But in ANOVA, we can have more than one independent variables. So with ANOVA, we are comparing several means rather than just two means. And we can use ANOVA when we have uh, manipulated more than one independent variables. So when we say manipulation, it means we can infer causality. And it is an extension of regression or the general linear model. Why not use lots of t-tests? So if we want to compare several means, we can use t-tests. But here is a problem. First of all, with t-test, we cannot look at several independent variables. But with ANOVA, we can have more than one independent variables. In both cases, we have only one dependent variable. Remember that with ANOVA, with one-way ANOVA, with two-way ANOVA, with independent t-test, we have only one dependent variable. But with t-test, we have only one independent variable. But with ANOVA, we can have more than one independent variables. In other words, if we want to run, let's say we have more than one independent variables, we can use multiple independent t-tests, but we are inflating the type 1 error rate or alpha error. So therefore, it's better to switch to ANOVA instead of like running multiple independent t-tests and then correct for type 1 error. So the hypothesis in ANOVA, so we have null hypothesis and alternative hypothesis. So in null hypothesis is that the means are all equal. So H0 or null hypothesis is mu1 equals to mu2 equals to mu3 equals to mu k, depending on how many groups we have. That's our null hypothesis. So the means are all equal. But the alternative hypothesis is that at least, this is very important, that's why it's in bold, at least one of the means is different. Or at least two means are different from each other. So in alternative hypothesis, in ANOVA, let's say we have three independent groups. In order to have an alternative hypothesis, it doesn't necessarily mean that we should have all different means for our groups. If we have at least one of the means different from another means, that's our alternative hypothesis. They don't all have to be different, just one of them. Just one of the means can be different from other means. That's what we are looking at. So let's say this is another example. This is another example from the POP example. We have a statistics classroom. And we divide that classroom into 3 rows: front row, middle row, and back row. The instructor noticed that the further the students were from him, the more likely they were to miss class or use an instant messenger during class. And let's say his research question is to see if the students further away did worse on the exams. This is an important point. The ANOVA does not test that one mean is less than another, only whether they are all equal or at least one is different. So in other terms, if we run ANOVA, we can say, okay, the means are different from each other if it is significant. If ANOVA is significant, we can conclude that the means are different from each other. But can we find out which mean is different from other means? We cannot do that with ANOVA. So we have another like additional test to test for that, to see which means are different from each other. So ANOVA does not test that one mean is less than another, only whether they are all equal or at least one is different. So this is our example. And this is our test scores: front, middle, and back row. So a random sample of the students in each row was taken. The score for those students on the second exam was recorded. So we have row. If you look at the table, we have row, uh, front, middle, and back. We have sample size for each row, and we have mean of the scores and standard deviation of that score, and the variance of that score for each column or each row in the classroom. So in one-way ANOVA, the question is, are all of the values identical? So that is our null hypothesis. Are all of these means are equal? That's our null hypothesis. So, but from here, from this table, we can say the means are different. They are not equal. But are they different statistically, or is the difference between means statistically significant? That's our question. We cannot assume that our means are statistically significant. I mean, the means are different from each other, and that difference is significant. We cannot assume that just by looking at the means. You know what? You know why? Because the standard deviation for the front row is 17. So if we do like mean plus minus standard deviation, the lower end of the mean will be similar to the back row. So this is why we have to run ANOVA, either by hand or using SPSS. And then we can find out whether the differences among means are statistically significant. So are all of the values identical? That's our first question by looking at the data, by looking at the table. No. So there is some variation in the data. This is called the total variation. We denoted that as SS total or SST, which represents total variation in the data. And sum of squares is another name for total variation in the data, sum of squares. So variation is the sum of the squares of the deviations between a value and the mean of the value. That's the variation. That's the definition for variation in the data. And sum of squares is abbreviated by SS, and often followed by a variable in parentheses such as SSB or SSW. So SSB is sum of squares between, and SSW is sum of squares within. So we know which sum of squares we are talking about. Are each of the values within each group identical? So let's look at the data. The front, the middle, the back. So no, there is some variation within the group. So for example, for the front row, we have a score of 53 and we have a score of 97. So we have a variation within groups. For the middle row, the score for the exam can be from 51 to 83. So we have a variation in the score in middle row. For the back row, we have also some variations from 38 to 66. So are each of the values within each group identical? No, there is some variation within the groups. That is called the within group variation, or sometimes called the error variation. And we use SSW in order to represent for that variation, or sum of squares within the groups. So we can create another table. So here we are trying to conduct ANOVA by hand instead of using SPSS. So we have between, within, and total. So we have two sources of variation. We have the variation between the groups or the variation due to the factor. The factor here is group. We have three groups. And in other words, we have three factors here. So the variation within the groups, or SS sum of squares within, or the variation that cannot be explained by the factor. So it's called the error variation. Grand mean. We saw grand mean in the POP example. So grand mean is the average of all the values when the factor is ignored. So the grand mean is the average of all of the values in our data set, the average for all of the individuals in our data set. And grand mean is a weighted average of the individual sample means. And here is the formula for that. So if we plug in our values from the example, our grand mean will be 65.08. And remember, the mean has only one bar above the mean symbol, but grand mean has two bars just above the symbol. So the weighted average means we are using the sample size. So let's go back to this one. So for the front row, sample size is 7. And the mean for the front row is 75.71. So 7 multiplied by 75.71 plus 9 multiplied by 67.11 plus 8 multiplied by 53.50 divided by the total sample size. 7 plus 9 plus 8. So our grand mean is 65.08. Because we are multiplying the mean of each group by the sample size, that's why it's called a weighted average of the individual sample means. So we calculate grand mean before calculating the sum of squares between and sum of squares within, or our variations. So before calculating the variations between groups and within groups, we have to calculate the grand mean first. So between group variation, or sum of squares between, it's the between group variation That's the variation between each sample mean and the grand mean. So each individual variation is weighted by the sample size. So in order to calculate sum of squares between, in our example, it will be 1902 or 1902. For the within group variation, that's the weighted total of the individual variations. So in this case, we have to have degrees of freedom. So for the sum of squares between or between group variation, we just use sample size. So we are using sample size and we are subtracting the mean of each group by the grand mean and square it and then multiply that by sample size plus the second group plus the third group. But for the sum of squares within group, we are multiplying the difference between the mean and the grand mean by the degrees of freedom. The degree of freedom for each sample is one less than the sample size. For example, the degree of freedom for the front row will be 7 minus 1, 6. For the middle row, 9 minus 1, 8. For the back row, it's 8 minus 1, 7. So that's the degree of freedom for each group. So we plug in, so right now we are completing our table. So we just did sum of squares between and sum of squares within. And if we add these up together, we can get the sum of squares total or the total variation in the data. The degree of freedom is the same. So for the between, we have three groups. 3 minus 1, it's 2. That's our degree of freedom. So a degree of freedom occurs for each value that can vary before the rest of the values are predetermined. So for example, if you had 6 numbers that had an average of 40, we would know that the total had to be 240. 5 of the 6 numbers could be anything, but once the first 5 are known, the last one is fixed. So the sum is 240. The degree of freedom would be 6 minus 1 or 5. The degree of freedom is often 1 less than the number of groups. So we have 3 groups. The degree of freedom for between is 2. The within group degree of freedom is the sum of the individuals' degree of freedom of each group. So our sample size are 7, 9, and 8. So degree of freedom for within, it's 7 minus 1, 6 plus. 9 minus 1, 8 plus. 8 minus 1, it's 7. So it will be 21. And the total degree of freedom is 1 less than the total sample size. Our total sample size is 21. 21 minus 1 is 23. For the MS, or the mean of the squares, that's our third step in conducting one-way ANOVA. The variances are also called the mean of the squares and abbreviated by MS. So MSB or MSW, that's the mean of the squares between or mean of the squares within. So they are an average square deviation from the mean and are found by dividing by variation by the degrees of freedom. So for the means of squares for between groups, we are dividing the sum of squares between groups by degree of freedom for between groups. And we have to do that for the within groups and total. So the MS total is not the sum of MS between and within. That works for the sum of squares, but not for the mean of squares. The MS total is not usually shown. So that's why it is in red. So we just completed the third step. Right now we are in F statistic. The F statistic is the mean of squares between divided by mean of the squares within. That's all. So the F test statistic, and F test statistic is the ratio of two sample variances. The mean of squares between and the mean of squares within are two sample variances. And that's what we divide to find F test statistic. So for our data, F test statistic is 5.9. The F test is a right tail test, and it has a table. It has a table like t-test, and we can just look up the table and see if it is what's the p-value for that F. So here the p-value is 0.009, which is way less than the significance level of 0.05. So we reject the null hypothesis. The null hypothesis is that the means of the three rows in class were the same, but we reject that. So at least one row has a different mean. We cannot say which row is different from another. We have to do an additional test procedure. But here we can at least say at least one row has a different mean by looking at the p-value of the one-way ANOVA. So here we can say there is enough evidence to support the claim that there is a difference in the mean scores of the front, middle, and back rows in class. The ANOVA does not tell which row is different. We have to do post hoc test to determine that. So when I'm talking about between groups variability, what am I talking about? We are talking about variance. What does sum of squares between represent? It represents sum of the difference in the means of the group. What does mean of square represent? What does the F ratio represent? I'm going to leave these questions to you to find out the answers by searching Google or by just reviewing your textbook. So the null hypothesis in one-way ANOVA is just like a t-test. ANOVA tests the null hypothesis that the means are the same. But in t-test, we have two independent means. In ANOVA, we have more than two independent means. The experimental hypothesis is that the means differ. At least one of the means is different from other means. At least one of them. And ANOVA is an omnibus test. What does it mean? It means it tests for an overall difference between groups. It tells us that the group means are different. It doesn't tell us exactly which means differ. So just like the linear regression model, if the F value is not significant, there is no need to do a post hoc test. So if F value is not significant, it means the all means are equal. Statistically are equal. So there is no need to do post hoc test. So this is our conditions or assumptions for one-way ANOVA. So the data are randomly sampled. The variances of each sample are assumed equal. The residuals are normally distributed. And also our um, dependent variable should be at interval or ratio level. So before you run an ANOVA, you must conduct tests for homogeneity of variance, independence of observations, and normal distributions. The post-hoc test, there are different types of post-hoc tests, and we will see that in SPSS. We can choose just one of them and go for that. But you remember, we do post-hoc tests just in the case of the p-value is significant. So if p-value is significant, we can run post-hoc test. If not, there is no need to do post-hoc test. So post-hoc tests, as I said, there are different types. We have Newman-Coles test. We have Tukey test, Tukey honestly significant difference, or HSD test. We have Schiff test. We have Donnet test. There are different types of post-hoc tests, and we can just choose among them. Just choose one of them. The non-parametric test for ANOVA is Kruskal-Wallis test. In this case, dependent variable can be ordinal. The data are converted to ranks, which are then compared, and we are using Kruskal-Wallis test for answering the question, are these all the same? Just like parametric test for ANOVA. So one-way ANOVA is the parametric version. The Kruskal-Wallis test is the non-parametric version for one-way ANOVA. And if the the assumptions are violated in some way, we can just use non-parametric version for one-way ANOVA, which is Kruskal-Wallis test. So remember, before running ANOVA, before running one-way ANOVA, you have to test for the independence of observations, the normality distribution of the residuals, and the homogeneity of variance. So this is again the puppy test. I'm gonna skip this. Um, this is from your textbook on how to calculate the sum of square total, which I showed you that. I'm gonna skip these ones too. I'm gonna go to um, let's see. And these are some, kind of advanced statistics, and I don't want to do that here. Let's see. Okay, so that was all about one-way ANOVA. So if I wanna run ANOVA in SPSS, let's say our research question is the amount of total steps walked by participants differ between participants in different BMI categories. So BMI categories can have 3 or 4 categories or groups. So we can have normal BMI, overweight, and obesity, for example. Let's say we have 3 BMI categories. So we have 3 groups. Our dependent variable is total steps walked by participants. And that is total steps in SPSS. That's our variable. That's our dependent variable. So we need to go to Analyze, click on Analyze, Compare Means, and One-Way ANOVA. After clicking on the one-way ANOVA, there should be a window like this. So we have independent list and factor. Our factor is BMI category. Dependent is the total steps. So in our research question, why is it a one-way ANOVA? Why we choose one-way ANOVA rather than other tests? So first of all, as I said, we have one dependent variable. That's our total steps. And we have 3 groups. We have BMI categories. Our BMI categories is normal, overweight, and obese. So after moving the variables to the dependent list and factor list, we can click on the post hoc and we can choose one of the post hoc tests, which is we can choose any one we want, but most of the time we choose LSD. And under options, we click on descriptives and continue and OK. Continue. And also under options, we can choose the homogeneity of variance test. We can also test for that here too. This will be our SPSS output when we run one-way ANOVA. So based on looking at the ANOVA table, so we will have descriptive statistics indicating the mean, standard deviation, standard error, the sample size for each group by group. And then we will have a ANOVA table, which shows our F value, F test statistics, along with degree of freedom, sum of squares, mean square, and significance or p-value. So based on this ANOVA table, the p-value or the significance is 0.001. That is way less than 0.05. So we know that there is a statistically significant difference between groups in the number of steps taken by different BMI categories. We also know that since the F value is 6.8, and by referring to our F distribution table, the critical value is 3.03. The F value exceeds the critical value and rejects our null hypothesis. So we are rejecting the idea that BMI categories would have the same or similar total number of steps, and accepts the alternative hypothesis that different BMI categories have different total number of steps associated with them. So since our p-value is significant, since our F-test statistic is significant, it's less than 0.05, we can do post hoc test. So here we have our post hoc test output in SPSS. The table for post hoc test is titled multiple comparison. So here we are comparing our three groups one by one for each rows. So for example, if you look at the output table here, we have BMI category normal. So we are comparing normal to overweight, and we are comparing normal to obese. And we can look at the p-value or significance column to see if there is a significant difference between each group, between two means. So there is only one, only two p-values that are significant. They are less than 0.05. So overweight and obese. So we can say there is a significant difference between overweight and obese BMI category in terms of the total number of steps. And the third row, it's obese and overweight, which is the same. You are comparing overweight with obese or comparing obese with overweight. Those are the same concepts. So we can also see the statistically significant differences between total steps walked and BMI category really occurred between the obese and of the overweight categories. So we accept the alternative hypothesis here, which means there is indeed a difference between participants' total steps. And as I said, we can just look at our descriptives, like looking at the mean. So these are the mean of the total steps. So we already know that there is a significant difference between overweight and obese. So overweight is 1,600,000 something for overweight, but for obese it's 1,300,000 something. That's the total step for obese BMI category. How to report results in APA format. This is the template for how to report the SPSS outputs for one-way ANOVA in APA style. I would like you to follow this template. So you can start by a one-way ANOVA was performed to evaluate the relationship between independent variable and dependent variable. The means and standard deviations are presented in table number below. And we can have a descriptive statistic table just like this. So you will have group 1, group 2, group 3, and the mean and standard deviation for each group. We can say the ANOVA was or was not significant at the alpha level. And then we can report the F. F, inside the parentheses, you have to have a degree of freedom between groups. And the comma, degree of freedom within groups, close the parentheses, and you report your F test statistic, comma, your p-value. And if you find a significant result, then you have to have a post-hoc test. So you can say a post-hoc two-key HSD test or a post-hoc LSD test indicated that the mean of the group X was significantly higher or lower than, and blah, blah, blah. Just like you can just follow this template. And where you can get these numbers like number 4, 7, 6 from the SPSS output. So as a summary, the statistical procedure that compares data between two or more groups or conditions, we use ANOVA. It is rarely used for two groups. So t-test is more common with two groups. Our purpose is to investigate the presence of differences between those groups. Dependent variable is continuous. It's either interval or ratio. And it computes two estimates of variances between and among. For your assignment for this module, you have to complete an ANOVA to answer the following questions. Number 1, does baseline BMI differ between participants who rated their health as excellent, very good, good, fair, or poor at baseline? That's one statistic procedure, one research question. You have to run ANOVA for that one. Why ANOVA? Because baseline BMI is a dependent variable, it's a continuous variable, and we have our independent variable is our health status, but we have more than two groups. So we are comparing the mean of baseline BMI by health status. The second question is, does FFQ differ for people who rated their self-rated health at baseline as excellent, very good, good, poor, or fair? So here you need to run a second one-way ANOVA to answer this research question. First, do the diagnostics or test assumptions. Second, determine what is the factor and what is the dependent. Third, if all is good, run the ANOVA. Here, I need to see your testing for assumptions for one-way ANOVA. But let's say if the test for assumptions are violated, I would like to report that the assumptions are violated, but I want to see you run one-way ANOVA rather than Kurzweil-Wallace test. And if your F test statistic is significant, I want to see your post-hoc test. And this is the table, for example, your table for one-way ANOVA. This is the APA style. And I want to see this. All right, this is our SPSS. I'm just gonna show you how to do that. So how to run one-way ANOVA. So I'm gonna skip the assumption testing. That's what you have done so far for each module. So I wanna see your assumption testing as well. So let's say I wanna run one-way ANOVA. My research question is whether the total cholesterol at baseline differ by uh, let's see what variables we have. Differ by education levels or differ by race. Let's go with race. So I'm gonna see whether total cholesterol at baseline differ by race. So I need to run one-way ANOVA. Why? My The total cholesterol at baseline is my dependent variable and it is a continuous variable. It is ratio level. And my independent variable are my groups, and my groups are by race. So I want to go to analyze, compare means, one-way ANOVA. So here I need to put total cholesterol at baseline under dependent list, and the factor is race. Okay. And then I don't need to worry about the contrast. For postdoc test, I'm gonna click on LSD and then continue and options. I just wanna click on the descriptives and homogeneity of variance and continue and click OK. Let's see. Oops. Um, okay. So this is the output you will see here. So this is descriptive. So I have the mean for total cholesterol at baseline for each race categories. The standard deviation for that, standard error, 95% confidence interval, and minimum maximum for total cholesterol for each group. My groups are like Mexican American, other Hispanic, non-Hispanic white, and Hispanic black, and so on and so forth. I have the test of homogeneity of variance. So based on median, the homogeneity of variance is not significant. So that assumption is met. So the homoscedasticity or the tests of homogeneity of variance assumption is met. For the ANOVA, that's the table I will look at. The F-test statistic is 1.046. The p-value is 0.384, which is not significant. That's way above 0.05. Because the F-test statistic is not significant, I don't need to look at post-hoc test. But if it was significant, I would look at the post-hoc test. But here I can report the F-test statistics by using the degree of freedom and the F value and then P value. This is the ANOVA effect sizes, so you can also report the effect sizes. But since it is not significant, there is no need to look at the effect sizes either. But let's say my F-test statistic is significant. So let's look at the post-hoc test. So here, since the the F-test statistic is not significant. So you will not find any significant p-value under the column significance test. There is no significant p-value here. If it was, the F-test statistic would be significant. But here we are comparing Mexican American with other Hispanic, non-Hispanic white, non-Hispanic black, and other race. The second row, we are comparing other Hispanic with Mexican American, non-Hispanic white, non-Hispanic black, and so on and so forth. That's the way we are. That's the way how we look at the postdoc test table. So that is all for module 8, and that's our last module. Please read the textbook and watch the lecture video, and do not hesitate to reach out if you have any question. Thank you.